we have talked about the relative frequencies. Now we're going to continue with the finite sample spaces and events with equal frequencies. What we talk about here is first the simple events, the events that consist only a single element of sample space, like suppose that you have a sample space of k elements, for example, like yes, your sample space, and you will have k elements in it. And what we talk about here is a set like this from A1, A2 to AK, namely, and you will have an event here, namely, for example, A. It's suppose that it is a J or something like this. Then these are the properties, like their probabilities of those events should be equal to or greater than 0 from 1 to k. You will have different elements here, and when you add all of these together from P1 to pk, you will end up with 1. That's the idea. And here you can just go ahead and write PA equals PAG, for example, and it will correspond to PJ. That's the idea. So suppose that again, yeah, if an event is, let me just clear here. If an event is like this, like A1, A2 to AR, then probability of that event will be the addition of all those events. So it's up to PR. That's the idea. For example, let's make an example here. If your S is, for example, A1, A2, and A3, for example, and your P1 equals 2P2 and P2 equals 2P3, for example. These are the possibilities for all of the corresponding elements here. So your P1, P2, P3 should be 1. This is coming from the properties. And then you can conclude that here I have, for example, 7 ports or 7 units here for satisfying the relation between those elements, probability of relation, and you can conclude that if your P3 is 1 over 7, if your P2 is 2 over 7, and if your P3 is 4 over 7, when you add them up, you can satisfy this, which gives you the idea about the simple events. When we're dealing with the events with equal frequencies, we must be really careful because some of them are not like this. I mean, we cannot assume, for example, the blood types can happen with equal frequencies, for example. So, I mean, because how do we say this? Because when you pick a random person from the population, the probability that he is, for example, a particular type of blood is directly not 1 over 4 because they are not having equal frequencies. So if you have, for example, if your S has k elements with equal frequencies, then your pi is 1 over k. And if your event A has R elements, and if your event A has R elements in it, this is small r elements in it, then that probability of that event will be directly R times 1 over k, each of the elements, and it corresponds to R over k, for example. So that's the idea about the events with equal frequencies here. You count the number of elements here, number of elements in A over number of elements in your sample space. So what can be some examples in this sense? So for example, a fair die. What about a fair die? Fair die for getting, for example, something above 4. So the thing is, what you can have here, either 5 and 6, and what are their probabilities separately? 1 over pi, right? It's 1 over 6 plus 1 over 6. You will end up with 1 over 3. That's one of the examples from the textbook. And another example again from the textbook. Suppose that, now that's where you need to be careful. It's a fair coin tossed twice, and 4 tails. What is the probability of having only 1 tails as the outcome? So you need to define the sample space here carefully. That's the idea. So I'm writing here. So what is the possibilities of having tails here? You can either have 0 tails, or you can have 1 tails, or you can have 2 tails at all, you see? So you can have 3 different elements here in this one, and each of them with equal frequencies, right? So then can you conclude that the probability of getting exactly 1 tails is 1 over 3? Pause the video and think about it. And now, if you, that's what I was telling you about the events with equal frequencies. You need to set your sample space carefully here, because in fact in this case your sample space would be something like this, like heads heads, heads tails, tails heads, and tails tails. This is the real, or the sample space that should be. So this is something wrong, and it would get you to wrong conclusions. Then okay, now these are the events with equal frequencies, and you can now come up with 1 over 4 plus 1 over 4, which is 1 over 2, would be your correct answer, right? This one and this one added together will give you the correct result. That's where to be careful about. So we should also be careful about the equality of probabilities, as we discussed, and we should be careful about defining sample space as well. Now sometimes you can, go ahead and transform a sample space into an equal probability one if it is not like this in nature. For example, suppose that your trying to create a equal probability atmosphere for picking a bottle from three different size bottles from a bag. Suppose that one of them is larger and one of them is smaller, for example. Okay, like I mean, if you have a bag like this and the bottles are shaped like this, so it means that you will have, I mean, since their sizes are different, but instead of this, you write their, I mean, you give them some numbers and you just put their numbers written in piece of papers in a bag. It means that you're just forcing your environment experiment to be happening with equal frequencies. That's one of the examples given in the textbook, and what we call this is marking. And we should also be careful about the equality of different combinations of elements in an event as well. Suppose that you're trying to pick 3 people out of 5 people, and all of the combinations of those people should have equal frequencies as well. Like, I mean, suppose that you have 5 people here, like you have 5 people here, particularly these people, and if you are creating a commission or team of 3 people from them, I mean, if you have all the combinations here like A, B, C, D, E, so if you pick, for example, A, it doesn't, the probability of A, B, C should not be different from A, B, D, for example. So if, for example, there's a, I mean, conflict between B and D, for example, the probabilities should not be different. You should also be careful about this as well. So these are emphasized. Now, we know that we need to be careful about defining the sample space. We need to be careful about determining the number of events as well. And the number of elements in an event and total number of events of sample space have to be known to make the necessary calculations. And there are several methods for satisfying, making those calculations possible. I mean, let me try to explain this to you with the example from the textbook. Suppose that you have a box of pills, like a box of pills, which you know that there are 20 LSD pills in it and 80 aspirins within that box. Okay, 20 LSD and 80 aspirins within that box. And when, I mean, you assume that 10 pills are picked at random from that box. And how, I mean, half of the, what is the probability that half of them are LSD, for example? Okay, so you're curious about this. Now, you need to first determine how many different 10 tablets combinations can be picked here. So what is your sample space? How many 10 pill combinations can be picked? That's it. So you need to first define the sample space. And again, you need to also be careful about how many of them consists exactly 5 LSD. So this is again defining the number of events here. This is also important. And then you will divide them. It's obvious for calculating the probability, but there are different methods for calculating the number of events here due to the nature of your experiments. Like the first one is called the multiplication method. Okay, this one, the multiplication method, where I mean, usually those independent events can be done together here. Those can happen together here. So let me just write them. Those events can appear, let's say, appear together. So that's the case, and let's take a look at an example from the textbook. So suppose that a factory produces for example, a factory produces three types of vehicles, like for example automobiles, trucks, and buses, for example. Okay, a company that produce automobiles, trucks, and buses, and they also manufacture them in 4 different colors, for example, namely white, blue, red, and say another color, yellow, for example. Okay, so here you first decide on the type, and then it can be one of the 3 possibilities: automobile, truck, or bus, and each of them can have 4 different combinations of colors, right? White or black or red or yellow, and 4 of them for this one and 4 of them for this one, which makes it 12 combinations available here. This is called the multiplication method, where you multiply them, right? So 3 possibilities here times 4 possibilities here, you will end up with 12. So these are the independent events that can be done together, or that can be happening together. Like in the second one, or the addition method, we can briefly say that if those can not happen together, those alternatives cannot happen together, we add the possibilities here. So here, let's take a look at another example in this sense. Suppose that you're trying to go from city A to city B, and there are some transportation options. You can either go with bus, or for example with train. If you go with bus, for example, there are 3 different routes here that you can take, and if you go with train, for example, you can have 2 different routes that you can take. What is the total possibilities here with bus and with train? You will end up with 5 possibilities here, namely your symbol will be addition here, because I mean, if you go with train, for example, you cannot go with bus, so they cannot happen at the same time. Okay, so what about the permutations? Now, in permutations, usually we're curious about how many different orderings, how many different orderings possible within n elements, for example, okay? Within the elements of sample space. We're curious about this for determining the number of events. Again, we can go ahead and take a look at the examples given in the textbook. So suppose that you have three letters A, B, C, and what are the different orderings here? They can be like A, B, C, B, A, C, etc. How many different orderings you can have here? 6. But how do we find them? You usually put their possibilities in their corresponding slots here up to n. For example, 1, 2, 3. These are your slots. And now you can remember that ordering is important here. It means that your ABC is different from CAB. Be careful, these are different. Because if it is not different, like you're selecting a team or something, you cannot use permutations here. Then you should go ahead and use combinations, but we will see it later. But here we're talking about the experiments that the orderings are important. Now you show this like this, like for n, p, n. You have n slots to fill here from n elements, and n elements here, and you fill n slots here. For the first one you will have n different possibility for filling that slot. If you put here one of them, for the next one you will have n minus 1 possibility here, times, because they're happening at the combinations of them, they can happen together here, like you remember from the multiplication method. And for the remainings, I mean, you will have n minus 2 up to 1 here, which gives you a famous factorial, n factorial here. Like and so you can say that n Pn is n factorial, and this factorial, 0 factorial equals to 1, just for remembering. And if you limit the slots here for selection, for example, if you limit the slots for selection, so it means that you will not use all of the slots here, but up to here, for example, okay, up to R, for example, okay, this is what we're talking about. Like you're curious about, you will have n elements here this time, but you will have R slots to check for different orderings for them. So you can go ahead and write n factorial over n minus r factorial. Why? Because instead of going up to 1 here, you will go up to n minus r plus 1 here, right? So this is why you're dividing the n minus r factorial here at the bottom. Otherwise, before it was like what? And this was n as well, and you would end up with 1 here. But in this case, you need to divide it by n minus r factorial, and so it looks like this if you're limiting. Suppose that, let's just try to clarify this with an example. You use 5 flags for signaling, for example. Suppose that a person who works at an airport giving with signals with I mean using some flags, just raising different colors, for example. So how many orderings you can have here? You first raise one of the colors, then the other one, for example. It means that you have 5 flags, and you will have 5 flags for signaling here. You will end up with 105 factorial and 120 orderings possible here. But what if you're given the option to raise only 2 flags within a selection of 5 flags? In this sense, again, you will have 5 flags here, but you're limited to 2 flags for that. It means that you will have 5 factorial over 5 minus 2 factorial, and it corresponds to 5 factorial over 3 factorial, this over this, and only 20 different orderings possible here instead of 120 if you limit your slots or ordering slots with 2 in this sense. Okay, I hope you have an idea about permutations. Now the combinations are, we already mentioned about this here, where orderings are not important this time, in these sets, in these sets of elements. Now let's go ahead and give an example about this from the textbook, like drawing. We already mentioned about this drawing pills from for 5 LSD, for example. Okay, in that example, you remember from a few moments ago, right? From a box of pills where it has 20 LSDs and 80 aspirins, right? So you draw 10 of them, and you have 5 LSDs in it. Or you will have an example of tossing 2 coins for having exactly 1 tails in it. 1 tails in it, right? Now, okay, now we will have here again n elements. Okay, n elements, and again we will have the slots available here, and this time you will have here, for example, okay, r slots again, but this time the ordering between them, like the r factorial, is not important, you see. So it means that you need to put this in the divisor part as well. So what will we end up with? So having p and r was, what was it in this time? N factorial over n minus r factorial, right? So this was like this, for where ordering is important here, but if it is not important, you need to divide it by r factorial as well here. That's it. So it becomes, if you, of course this is not permutation anymore, but if you put here r factorial as well, this particular one makes it becomes your combination, and r n factorial over n minus r factorial. That's the idea. So it becomes your combination formula, roughly. And these are also called the binomial coefficients, right? And binomial coefficients. When you do binomial expansion here, and you show them with an r, and when you try to expand this, you will have terms like a over r, d over n minus r terms. And what are the coefficients of these terms? Are coming from here, the combinations, and you can write them generally, or you can generalize them like this, from r 0 to n combination of, these are the coefficients from the combinations, a over I, b over n minus r. That's how you generalize them. The thing about them is those binomial coefficients, they're symmetric as well. Symmetric. So it means that your nr will be equal to n minus r as well. So that's it, like 6, 4 equal to 6, 2, for example, combination of that's it. Okay, now let's try to work on some examples to clarify the combinations. These are the examples from the textbook. Suppose that you have n equals 8 people and you are trying to form 3 people teams from that 8 people. And how many different teams can you have here? It's pretty straightforward, right? The combination of when you apply this, 8 over 8 minus 3 factorial over 3 factorial, which would give you 56. That's it. So another example, again from the textbook, you have a box of 100 bucks, 100 pills in it, in the box. And how many different 5 pills can be drawn from that box? Okay, so it means that you can have this much of pill. Maybe you remember this from our previous session, right? We discussed this examples and write their combinations directly, but this is where we calculate them. 95 factorial, 5 factorial, and it would give you, if you remember from our previous session, those were the numbers that we write directly. And the last example is again from our previous session. If you have a 52 card deck, how many different 13 hands possible from that 52 card deck? So you can again calculate it directly like this. So this factorial over, okay, they are very ugly, but thanks to our calculators we can calculate them in a few steps, hopefully. 35013 559 and 600. With this many combinations of 13 hands are possible here. So that's the idea. Now we usually have mixed forms as well, where we combine all of them together, where required, but carefully, of course. And let's take a look at some examples to understand where they can be useful. For example, suppose that you have 5 males and 3 females, and you're trying to form teams of consisting 2 males and 1 female in them. Okay, how do you do it? You have 2 slots for males and 1 slot for females, right? So it means that for male slot I need to choose 2 different people from 5 people in how many combinations, and for the females pretty similar, and I multiply them because these events will be happening at the same time, right? These events will be happening at the same time, so you will end up with 30, where you have this is the mixture of combination and multiplication, right? Multiplication method. Okay. And what else? If we return to our original example that at the start of this session, 5 LSD from this box, 20 LSD and 80 aspirin box. When we pick 10 pills here, what is the probability of having 5 LSD? Okay, now we first need to determine the sample space, right? We already have an idea about the sample space here. It should be like a combination of how many different combinations of tens taken from 100 pills. Then you need to define the event, like events. You need to have your event is you need 5, exactly 5 from that 20, and the remaining 5 should be aspirins, okay? And you multiply them because it's a mixed form. This is your event, and the probability of that event will be eventually this one times this one over your sample space. You see, this one is coming from here and this one is coming to here, and the result, when you make the necessary calculations, please do on your own. Pause the video and do on your own if you like, and the probability will correspond to this, and this is how we, like, roughly 2% probability. That's the idea with the mixed forms.